We all kind of think of AI models as these giant monolithic black boxes, right? We train them, we talk to them, but we don't really know how to get in there and tweak their core abilities. But what if we could? What if we could perform a kind of brain surgery, precisely pulling out a specific reasoning skill from one AI and literally transplanting it into another? That is the incredible, mind-bending possibility we're diving into today.
So here's the game plan. First, we're going to break down the hidden flaws in how today's AIs actually think. Then, we'll introduce a brand new concept called the Cortex. Think of it as a specialized brain for AI. From there, we'll get into the wild idea of neural gene transplantation, see how that surgery would actually work. And finally, just imagine the incredible future this could unlock for AI design.
Okay, so let's start with the problem. Large language models, LLMs, they're amazing at so many things. But when it comes to pure, step-by-step logical reasoning, their basic architecture has some pretty serious baked-in limitations.
These limitations really fall into three buckets. First, you've got the lock-in problem. A tiny change at the start of its thinking can send the AI way off track into a completely wrong answer. Second, they don't have what we call graceful degradation. They don't get a little worse, they just fail hard. And third, the sequential bottleneck. Because they think one word at a time, any complex reasoning is just inherently slow.
To really get that second point, just think about an AI image generator. If you tell it to use fewer steps, you get a blurrier, kind of lower res image. But it's still the right image, right? Well, with an LLM, if you cut it off, you don't get a lower resolution answer. Their reasoning just hits a brick wall, making the whole thing totally useless. There's just no smooth way to trade speed for a little less precision.
So at the end of the day, we're really hitting an architectural wall here. And that brings up the big question. If the way we're doing things now has these deep, fundamental flaws for pure logic, what's the alternative?
And that leads us to the proposed solution, a concept called the Cortex. The big idea here is to create a specialized, super efficient reasoning engine that works in a completely different way from the LLMs we're all used to.
So what is a cortex? Well, imagine a reasoning core that does all its work in latent space, that abstract mathematical world where an AI really gets concepts. All the heavy-duty logical work happens there, all at once, deep under the surface of the words. The language part? That just becomes the user interface for this powerhouse of a reasoning engine.
And wow, the contrast is just night and day. Current models, they're stuck going token by token, they're sequential and slow, trying to cram these big ideas into clunky individual words. The Cortex, on the other hand, would operate in that fluid latent space, making it parallel, incredibly fast, and able to work with much richer, continuous ideas of logic.
And the potential speedup we're talking about, it's not a small improvement. It is absolutely massive. Getting reasoning out of that word-by-word traffic jam and into a parallel latent space engine is a total game changer for performance.
Okay, so a fast, efficient reasoning core sounds amazing. But how on earth would we even build it? Well, this leads us to a truly radical way of thinking about it. What if AI abilities were like genes that we could actually engineer?
This quote from the source material just perfectly captures the ambition. It's about getting past just training AI and moving to a world where we can operate on them like surgeons, snipping out a functional gene for a specific skill and just moving it somewhere new. And this is a huge change in thinking. A skill, like being good at logic, isn't just some vague behavior spread out all over the network. The idea is that it's a specific functional circuit of neurons and weights that, if we could just pinpoint it, we could isolate, extract, and literally transplant.
The whole metaphor gets way more concrete when you map the pieces. A biological gene is like a functional circuit in the AI, and the promoter region in our DNA that tells a gene when to turn on, that's just like the trigger conditions in the network that tell a specific reasoning circuit to fire up. It maps almost perfectly.
So if we can identify these circuits, how do we actually do the transplant? What are the real, practical steps for this AI brain surgery?
It really boils down into three key steps. First, you capture the signature of a skill. You watch which neurons light up in a powerful AI, kind of like creating an activation heat map. Second, you take that circuit and move it into a new host model, adding some tiny adapters. Third, and this is the absolute key, you train only the adapter until the circuit, in its new home, produces the exact same heat map as the original.
That activation signature, that's the secret sauce. It's the functional blueprint. You're not just crossing your fingers and hoping the transplant works. You're giving the new model a precise target to aim for. The whole goal is to perfectly replicate the functional pattern of that original circuit in its new home. So what exactly are these adapters? Well, think of them like a universal translator. A neural circuit from one model speaks a slightly different internal language than another. The adapter is just a very small, trainable layer that figures out how to translate the inputs and outputs so this foreign circuit can plug right in and communicate perfectly with its new host.
So, what's the upshot of all this? If this technique actually pans out, it does more than just give us faster models. It completely changes how we design and build AI from the ground up. It signals the dawn of what you might call composable AI.
And let me be really clear. This isn't just another incremental improvement. It represents one single massive shift in how we do things. It's a completely new paradigm for developing AI, moving us away from discovering intelligence and towards actually designing it.
This just blows the doors open to a fascinating new era. We could start building AIs by snapping together pre-existing, proven capabilities, kind of like Lego bricks of logic. You could even imagine capability marketplaces, where a developer could go out and buy a best-in-class reasoning circuit to transplant into their model. We stop being AI trainers, and we start becoming AI engineers. That's the heart of it, right there. For decades, we've been like trainers, trying to encourage the right behaviors out of these mysterious black boxes. This approach basically puts the blueprints right in our hands. We're not just trainers anymore, we're becoming AI architects.
And this isn't some science fiction idea that comes out of nowhere. It's actually a pretty logical evolution. Today, we train these huge single models. We're already messing around with merging models and using adapters. The vision of building AI from transplanted circuits is just the next dramatic but totally logical step on that journey.
So the crucial point to take away is that this isn't just about making AI a little bit faster or more efficient. This is a technique that could fundamentally change everything about how we build, scale, and even think about artificial intelligence.
And that leaves us with one last massive question to think about. We spent all these years learning how to train AI brains. What happens to our world and to the future of intelligence itself when we finally learn how to design them?